Hello everyone, this video is titled Topic Recap on the properties of giant ionic compounds. So we will look at really quickly just the basics of ionic bonding. We will then look at how that ionic bonding dictates the structure of these compounds, and then we will link the structure and the bonding to the properties of these giant ionic compounds. First of all, let's just look at sodium chloride. So, very common example used in exams and in your textbooks, etc. You have a sodium ion with a positive charge. You've got your chlorine ion with your negative charge. You can see here that what's happened is the outer shell electron of sodium has transferred here over to the outer shell of chlorine. They've both got full shells. We form negative and positive ions. Now, that would be... if they said show the bonding in sodium chloride, there is what you would draw. In reality, what we actually have, which we don't always demonstrate in these types of diagrams, is we actually have an electrostatic attraction between the two ions. And this attraction, as I said, I'll write down the word, is a strong, I'll put that in brackets because they're actually called electrostatic forces of attraction. Okay, and they are strong. So between two oppositely charged ions, they will kind of attract together like a magnet. So when you hold two opposite poles of a magnet in close proximity to one another, they attract. Okay, and this is very similar with ions. When they are in close proximity to one another, an oppositely charged ion will attract to the other ion of the opposite charge. Okay, so rather than us ever call it magnetic attraction, which we will not do, we will always refer, because the reason we don't reuse magnetic is because we're not talking about magnets. We are talking about ions, and ions have electrostatic forces of attraction. Now, in reality, if you were looking at any amount of sodium chloride, you wouldn't just have one sodium ion and one chloride ion bonded together. What you would actually have is diagrams like so. Okay, these are just two examples. Again, quite often these examples are used. So rather than just have one ion, one positive and one negative, we actually show them formed in what we call a giant ionic lattice, or a giant structure of ions. Okay, so you actually have lots of positive ions and lots of negative ions, all interactive with one another. And when they interact with one another, they arrange themselves in a lattice. So if that question was ever asked to you, how are ionic compounds bonded together? What is the arrangement of these ionic compounds? You would say ionic compounds are held together by strong electrostatic forces of attraction. And I'm just going to highlight there because it's a key word. Strong electrostatic forces of attraction between oppositely charged ions arranged in a lattice. Okay, you can see there that the words I've underlined are key words, and they tend to be the phrases that pick you up marks. Okay, so like I said, rather than just drawing one ion positive and one ion negative, we actually have lots of them, and they arrange themselves in an ionic lattice. And another way you can sometimes see these ions drawn is 2D. So we just see positive ions. So again, this is just one model, really basic. But you just see positive ions and negative ions bonded together. So really what I've drawn here is a 2D diagram of this. Okay, so you have to understand that we can look at multiple models, but really we are all looking at the same thing. All three of those diagrams there show you these giant structure of ions, okay, or a giant lattice structure of ions. Now, the bonding that we looked at on the first slide and the structure that we're looking at on this slide, we can use both of those to start talking about the properties. Now, the first property we're going to look at is, first properties, should I say, are high melting and high boiling points, i.e. how much temperature is needed to be able to melt them and to be able to boil them. Now, ionic compounds have very high melting points and boiling points, and the reason being is that they have strong electrostatic forces between oppositely charged ions, and these require a lot of energy to overcome. Notice the word overcome here. Okay, we are not using the word break. Lots of times students write that, okay, and actually really it's not correct from a chemistry perspective. We want to talk about forces being overcome and bonds breaking. We're talking about electrostatic forces, so we will always talk about them being overcome. Okay, so the reason, again, what I'll do is I'll draw my basic 2D diagram that I had on the previous slide. So I just had ions lined up here in a regular arrangement. So I'm actually drawing solid sodium chloride here. Okay, and actually what happens is that all of these ions are obviously all attracted to the opposite charged ion next to it. Okay, so all of these forces of attraction act in all directions. That's sometimes something that you hear said. They act in all directions. Well, each of those red arrows is representing an electrostatic force, and each of those electrostatic forces is very, very strong. So therefore, having a large amount of strong electrostatic forces between oppositely charged ions means they have high melting and high boiling points, because each of those red arrows, each of those electrostatic forces has to be overcome for the structure to be melted or boiled. So if each of those forces each requires a lot of energy, it means the melting and boiling points will be higher. The last property we look at is the conduction of electricity. Okay, so ionic compounds can conduct electricity when they are molten or in solution. The reason being, when the when the ionic compounds are molten or in solution, ions are free to move. When they are free to move, they can then carry charge throughout the lattice structure. So again, I'll draw my really basic example. And as I said before, I was drawing it as a solid. So all of these ions tightly packed. Remember, this is a 2D diagram. So they're all tightly packed in this giant ionic lattice. Those particles are not moving. Okay, they're fixed in their arrangement. Okay, they've got strong electrostatic forces and they're fixed. Well, the minute you start to try and melt something, i.e. make it molten, or the minute you add water to make it a solution, those ions disperse and the forces are no longer referred to. Okay, so now all of these ions are now free to move. So each of them is now moving around in all different directions. And when those ions are free to move, they can carry charge. If they can carry charge, they can conduct electricity. So this is when the ionic compounds are molten or in solution. Remember, molten just means that they've been melted. Solution means they have had water added to them. And that's the three properties that you need to look at. I'll do a really quick summary. So we there just looked at the bonding and the structure of ionic compounds. Okay, in ionic compounds, of course, there is ionic bonding. Ionic bonding is looking at the electrostatic forces between oppositely charged ions. So if you have a positive ion and a negative ion, okay, next to one another, they're going to have electrostatic forces between them. Now, they are very strong. They require lots of energy to overcome, which is why ionic compounds have high melting points, MP, and high boiling points, BP. Okay, these ionic structures or ionic compounds, they're arranged in a giant lattice. The minute you melt that lattice or add water to it, these electrostatic forces are overcome. Okay, ions are now free to move and means that our ionic compound can conduct electricity. Okay, so when you're referring to high melting point and high boiling point, you want to be talking about strong electrostatic forces requiring lots of energy to overcome. When you are talking about conducting electricity, you must refer to whether the compound is molten or in solution. You then have to refer to the fact that ions are free to move and can carry charge.